Have you ever just stopped and wondered, why is anything solid? Why does the stuff around us, and even us, have substance? Why does it have mass? It seems like such a basic question, right? But for decades, it was one of the absolute biggest mysteries in all of physics. And the search for that answer led scientists to a wild new idea and a particle they would call the Higgs boson. I mean, really think about it. It's so fundamental, it almost sounds silly. But without mass, every particle in the universe would just blast around at the speed of light. You wouldn't have atoms or planets or, well, us. The whole cosmos would just be this thin, boring soup of energy. So figuring out mass isn't just some abstract quest. It's literally about understanding why we exist at all. Okay, so to get to the answer, we first have to talk about the problem. And for a long, long time, the problem was a huge, gaping hole in our best theory of, well, everything. So this right here, this is the standard model of particle physics. You can think of it as the complete cast of characters for our universe. You've got the matter particles over here, like quarks and electrons, and then you've got the force-carrying particles, the bosons, over there. This thing is unbelievably successful. Its predictions have been trusted and proven right with insane accuracy. But for years, it had one fatal flaw. And this is where the whole thing just fell apart. On one hand, you have the beautiful, elegant math of the theory. For all its symmetries to hold up, some of those force carriers, the W and Z bosons, had to have zero mass. But on the other hand, you had cold, hard reality. When physicists actually found these particles in experiments, they were massive, like really, really heavy. This wasn't some tiny error. It was a flat-out contradiction that threatened to bring the entire theory crashing down. No wonder they called it the central problem in particle physics. The solution, which was first kicked around way back in the 1960s, was, well, it was beautiful, profound, and honestly, a little weird. The idea wasn't to change the particles, but to change our understanding of empty space itself. So a few brilliant physicists proposed this totally radical idea. What if there's an invisible energy field that fills up every single nook and cranny of the universe? I mean, everywhere. A kind of cosmic molasses that's there even in the deepest, most perfect vacuum of space. And they called it the Higgs Field. This picture here really shows you why the Higgs field is so darn special. You see, for pretty much every other field in physics, the lowest, most stable energy state, its ground state, is zero, nothing. But the Higgs field has this funky sombrero shape. Its lowest energy state isn't up there at the peak. Nope, it's down in the brim, which means the universe actually finds it easier to have a non-zero value of this field humming along everywhere. And that leads to this just mind-bending conclusion. Because of that Higgs field, our universe actually settled into a state where it takes less energy for it to be something than to be nothing. Let that sink in for a second. This constant background hum of the Higgs field is what broke the perfect symmetry of the early universe, and, in doing so, allowed mass to pop into existence. So what this all means is that mass isn't really something a particle has like electric charge. It's something it gets by interacting with this universal field. Think of it like this. Some particles, like the super heavy top quark, really struggle to move through the field. They interact a lot, so they're heavy. Others, like the electron, interact just a tiny bit, so they're very light. And then you have particles like photons, the particles of light. They don't interact at all. They just glide right through, which is why they stay massless and can travel at the speed of light. Okay, that is a beautiful theory, but how in the world do you prove that an invisible, everywhere-at-once field actually exists? Well, quantum mechanics gives you a clue. Every field has a particle, so if you could just poke the Higgs field hard enough, a little particle, a Higgs boson, should pop out. And just like that, one of the greatest scientific hunts in human history was on. And, I mean, this was an epic search. We're talking more than 40 years. It spanned generations of scientists and required building these absolutely massive, ever more powerful machines. From the LEP collider at CERN to the Tevatron in the US, each one pushed technology to its limits, and each one came up empty-handed. The whole thing finally came to a head with the most powerful machine ever built by humanity, the Large Hadron Collider. 300 trillion. Just try to wrap your head around that number. That's roughly how many proton-on-proton collisions scientists had to smash, record, and sift through at the LHC to find what they were looking for. The Higgs boson is so incredibly rare and disappears so fast, finding it is like trying to spot one specific, identifiable grain of sand across all the beaches on Earth, and your only clue is a blurry photo of where it might have been a split second ago. But all that searching, all that mind-boggling data, all that human ingenuity, it all led to one of the most incredible moments in the history of science. So here's the thing. You don't actually see a Higgs boson. It exists for less than a trillionth of a second. It's gone before you could ever hope to spot it. So what scientists look for is the smoking gun, the telltale spray of other more familiar particles that it decays into. They were looking for very specific patterns in the wreckage, like this one here, showing a decay into 2 high-energy photons. The real challenge was proving this pattern was happening way more often than it should by pure random chance. And then came July 4th, 2012, in a packed auditorium at CERN with a tearful Peter Higgs, one of the original theorists, watching from the audience. Scientists from 2 totally separate, independent experiments announced to the world that they had seen it. The evidence was undeniable. After almost 50 years, the ghost particle had finally been found. And you have to understand, this wasn't just about ticking another particle off a list. Finding the Higgs validated the entire Standard Model, finally giving us the mechanism for mass. It also proved that a completely new kind of thing, a scalar field, which has a value but no direction, actually exists in our universe. Finding the Higgs boson wasn't just closing a chapter, it was the key that unlocked a whole new book. And that new book has some seriously wild plot twists. It turns out that the precise mass of the Higgs boson, around 125 times heavier than a proton, is a fascinatingly weird number. It places our entire universe on a razor's edge between being perfectly, eternally stable and just being metastable, which is a fancy way of saying we're living in a long-lived bubble that could, billions of years from now, collapse into an even more stable state. The very particle that gives our universe substance might also hold the key to its ultimate doom. So, the discovery of the Higgs boson answered one of the biggest questions we could possibly ask about reality. But like any great discovery, it just opened up a dozen more, even bigger, even deeper questions. What else is the Higgs hiding? What secrets about the cosmos will it help us unlock next? That is what physicists are trying to figure out right now.